Good morning, everyone. Welcome to One Topic, Multiple Tools, Multiple Learnings web series. And today we are going to learn something on constant forces, simulation tools that are used in constant forces like tension, friction, and buoyancy. These are the three forces that we'll be looking into it. And apart from it, we'll also be looking into the gravity component, which is your inclined plane. Okay, four forces will be looking into it, what kind of simulation tools one can use so that the students understand well, or we can depict these forces using the simulation tools. Okay, not every tool can be used, but some of the tools, wherever you need, you can actually use it. Okay, let me share my screen to show to you like how to be used this one here. So the first one to show with is, I'll just introduce all the different forces. To introduce the forces, what are the different kinds of tools we use? That's what I'm going to show you. The first one is about the force on an inclined plane. So you have an inclined plane, and any student in the beginning, when you ask them, okay, why does the cart actually comes down? Then the first thing is they say that, okay, the gravity acts on it. No, but actually gravity acts downwards. So why should it come down in this way? Then they will not be able to answer it, and they get stuck over there. Sometimes they say friction and so on. Many misconceptions are there. So the easiest way to explain this is nothing but, okay, so using this simulation tool from Java Lab. So what we do is, initially I can put it over here like this. I can move this slider over here, put theta equal to 0, and I see what is the force acting here. Mg is the force acting here, normal with the upward force. So the object does not move. Now, if I change this angle of the incline, now as a result of it, what happens? You see, there's a small component of the gravity which is acting here, which is 0.09 mg. Okay, and therefore the force is also very small. It may just start to slide. Okay, the force is lesser, so it may start to move a little bit more. So therefore, you see, so this is the length of the vector which is being shown over here, which is correspond to this. Okay, because when you're asked them to write the component of mg, sometimes they draw a very larger vector. So somewhere the component or the length of the vector should be proportional to the magnitude of the vector, right? So therefore, you have to draw a smaller one over here. Now, if I increase this angle, now what happens over here? See, this length has increased. Okay, this is equal to the length as you see, observe over here. Now, what is this curve over here? This curve is nothing but a plot of mg versus theta. Okay, sorry, mg sine theta versus theta. So therefore, as the value of theta increases, the value of mg sine theta also increases, go to a plateau level, and finally it starts decreasing. You will see both the ranges. How does it happen over here? So at smaller ranges, you see the length of this vector that I need to draw here should be equal to should be equal to this length over here. Now, if I increase this value, now let us say at this point, maybe if I keep it at this point, what is this value? This is 45 degrees. Let me keep it at 45 here. 25, 32, 38, 40, 45. If this angle of incline is 45, now this is 45 over here. Now you see the length of this vector is this much large, right? Definitely it starts sliding. So length of the vector is really large over here. Now, when do we reach this point? Okay, where is 60 degree? Okay, let us say 60. 60 should be somewhere over here. So this should be your length of the vector from here to this point. So let me make it 60, 56, 57, 60. 60 over here. This is the length of the vector. Okay, length of the vector is really larger when you come across here. Okay, now, so that means the force is also very high. It's around 0.87 times mg. It's not equal to mg. It's 0.87 times mg over here. Okay, but when will it be equal to mg? When it reaches this point. What do you mean by that point? That means it should be, angle should be 90 degrees. Now, let me increase it to angle 90 degree. So what do you mean by 90 degree over here? Which means the plane is exactly vertical. It is as if you are dropping the object from a height, right? So therefore, it is 90 degree over here. Now you can still go here, but unfortunately my slider doesn't work beyond this. Okay, so but if you go beyond this also, okay, so same kind of curve will be seen over here. So when I go beyond this, if the slider was much larger, if you, any one of you are an expert in using these kinds of JavaScript, okay, made tools, maybe are using GeoGebra, you can actually design this, and then what you can do is you make 130, 110 and so on. If you make 120, 110, what will happen? Now this incline would be much more like this over here. Okay, so you can try doing that also. Sorry, not this way. It will be like this over here. See, it's like this is 89, right? It's 80, 85 something over here. Okay, this is 90. If you make it 95, 100 and so on, it would be like this over here. Okay, and then 115, it will be like this, and 120, 130, 150 would be like this. Finally, 180 will once again be a flat, which is nothing but this point. Okay, so this is how you can explain Okay, what happens to the value of gravitational force when there's an incline? The gravitational force is seen to be reducing initially, it's seen to be increasing initially from 0, okay, and then the downward force seems to be increasing, and finally, okay, it becomes a maximum when you drop it from, when the angle becomes 90 degrees. Okay, next, let us go to how do we explain friction. Friction, we explain them as saying something like electromagnetic interaction, and then we say we take up two cubes, for example, attach each other, and then we try to pull it across. When we rub our hands, we show all these things, right? So similarly here also there are imperfections shown over here. There's one book, physics book here, chemistry book over here, and then you can bring this one down here. You can create this one here, you can pull it down over here, some PHET, okay, pull it down over here. Initially you see temperature is minimum, some value is shown over here. Now when I brush this, what do you feel? You feel heat, right? Which means what? The temperature should increase. Now brush it across here. You see, temperature has increased. Okay. Now temperature is increasing over here. And now what happens is if I keep on brushing it constantly, what happens? Now what has happened? The brushing has now changed. So automatically the object is now able to move. See, I can easily move. When the friction is very, very high, then some of the imperfections on the surface has been lost. Right? That's what it means. Okay, and then later on temperature reduces, and now, okay, so imperfections lost, so you'll be easily able to move across here. This explains your static friction and as well as your kinetic friction also. But of course, it doesn't give you an exact value over here, but it says, okay, the imperfections have been lost, are been broken, or how, or rather than you can say all this, you can say how friction gives rise to a rise in temperature. Okay, so when you rub across two surfaces, how does it give rise to rise in temperature? That's what you can say here. Okay, it doesn't give you any measure over here, how many times you have rubbed, what is the rise in temperature, nothing can be shown over here, but at least to showcase what's happening, okay, during an electromagnetic interaction, you will be able to use this particular video. Okay, next. Now shown here is about a friction lab. Okay, now what I'll do is I'll reset this. So there is an object over here, and it says surfaces are rubber on ice. There's a rubber and there's an ice surface, and the mass has been given over here. Okay, and then there's a graph also given here. Okay, now I can increase the mass, I can decrease the mass, whatever I want. Let me decrease it initially, make it 144 grams initially. I'll start with this. When I start this, and I look at the graph here, this is the force. This is the force in Newton, and this is the, so this is a frictional force, and this is the applied force, and versus what is there over here. This is your time in seconds. This is time in seconds. Okay, so time in seconds. As the time increases, what happens over here? Okay, you're not able to see the full thing. Let me reduce it. Okay, here it's fine. Let me restart this. So I kept 144 grams. I'll give a start here. So as you see, as the force increases at a particular point, at this point, the rubber object starts moving over here. Okay, and as it starts moving, this force remains a constant. That is, the frictional force remains a constant. That's what it tells you over here. So initially from here to here, this is a static friction where the applied force and the frictional force are equal, and this happens until a certain time. And after that, there's a limiting friction reached, and then it comes to a kinetic friction. This is what it can be shown. Okay, so this is nothing but we usually explain it using a chalk and talk way, but you can also do it using this method. Then let's move on to the next one. So this one is nothing but we have seen this already in our Newton's laws of motion video, and the same experiment, the same PHET, I'm not showing it over here. So what you can do is you can actually change the friction here. There was a slider here, and using we actually put the friction to be 0 here, but if you increase the friction to some value over here, so definitely the object will slow down. You will be able to find out what is the change in speed, all this. And there are some questions over here. These questions are really good. Okay, you can ask the students to look at these values, how to arrive at the coefficient of friction. Once the theory has been taught, we can ask them to work on all this also. Okay, now let us move on to the next one. This one is about one more software or web tool, which tells you about friction. Okay, so now what we do is, let me say friction off. Initially, when I say friction off, and how do I move this? Air drag is also off. Okay, and then what I can do is I can increase this normal force, about normal, increasing the normal force, which means I can increase the value of this. Okay, let me click here. I'm giving some force. I'm applying a force over here. Frictional force is also equal to so much. Just a moment. Let me see what is missed. What am I missing here? Okay, there is a, okay, let me put this off first. Let me put both of them off initially, and I'll put this to be 0. I'll put this to be 0. And maybe I'll restart this. Started somewhere in between. I'll restart this. Okay. Now initially the slider here who is on the sledge is now it is at rest. The friction is off. Air resistance is also off. Okay. He has some weight and normal force is equal to so much. Now if I give a small velocity here, if I give a small push over here, 20 Newton. Now what do you see here? So I am applying the same constant force throughout. The velocities seem to be increasing. Okay. The speeding is seen over here. Now what I do is I'll make it to be 0 initially. Now when I keep it at 0, net force is 0, the velocity seems to be a constant. Velocity does not increase. Now I want to introduce friction here as a friction arm. Okay, and how much friction is it? 50 Newton. So that means I have applied a brake, and as a result of this, okay, this person has now come to rest over here. Okay, now what I'll do is let me increase the force once again. Okay, friction is like this. Since the friction was like this, if I apply a force in this direction, now you can ask the question, if I apply a force like this over here, do you think the object will slide? The object will not slide. The reason is because okay, friction will act in a direction opposite to oppose the relative motion. So therefore net force is 0. Now let me increase this. See, applied force is equal to minus 40 Newton because it's in this direction. Frictional force also 40 Newton. Let me increase it a little bit. Minus 60 Newton, frictional force 50 Newton. Earlier also you've seen frictional force only 50. Now what is the excess surplus of it? Is nothing but minus 10 Newton. That means there's still a force minus 10 Newton over here. And as a result of it, the object's velocity is increasing in the negative direction. You see, the velocity is increasing in negative direction. Now to stop this, what I should do? Friction, I cannot do anything. So I need to put an air drag on over here. I need to put a parachute, right? Let me put a parachute over here like this. So when I put a parachute over here, now what's happening over here? What is the parachute's resistance? 8 Newton over here. Here it was 60, here it was 50, 50 plus 8, and then see it's increasing here. 1 Newton is increase, right? Earlier it was 8, now it was 9 over here. Why does it increase? You can ask this question. You can say reason is because the air drag is proportional to the velocity when the person's velocity, when the person's velocity is moving slower. Okay, but on the other hand, if it is much faster, it's proportional to v square. Now it's only proportional to velocity, so that's how. Okay, as the person is moving, so this is what is happening over here. See, now it becomes 50 plus 10, and thus the velocity does not increase over here, right? So you can ask these kinds of questions. You can ask them to work on this also. Okay, now let me increase this a little bit. Okay, now the force I have increased. What is this plus 1 over here? The weight I have increased. Normal force I have increased. When I increase this, then what happens over here? Okay, the velocity seems to be decreasing. Why does it decrease? The reason is because mu times n will now increase, right? Mu is not increasing. N increases as a result of it. Mu times n increases. Now when mu times n increases, now once again what happens? This was seen to be 10 Newton. Now this is seen to be 4 Newton. Why did it decrease? See, it decreased, then it remained a constant. Now once again the velocity seems to be increasing. Okay, and once again it reduces. So there's a chaotic thing that is there. Okay, so what you can do is you can ask the students to look at these readings, plot a graph of it, right, and then understand what is the mechanics behind it. Okay, that also can be done over here. Okay, so wonderful tool as such. If you want to do something on data analysis, one can really do a lot of work on this. Okay, next, let us go to the next one. So far we have seen about inclined plane, we have seen about frictions, how does it work, and air resistance. The next is about the tensions. So shown here is an example of an Atwood's mission. Okay, Atwood's mission is nothing but you put a pulley and you put two objects over here, and then you increase this object, and as a result of it, one object's mass, this object comes down, this object is being lifted upwards. That's what Atwood's mission does. You can do it in your school also, a similar kind of mission, and find out, okay, what time does it take for one object to come down. You find out the acceleration, tension. So all these things you can do it over here. Now what I will do is let me increase one of the masses over here. This is 1 kg, this is also 1 kg. Let me increase one of them. I'll make it 1.1. So what do you expect? What do you expect over here? So this should come down. Okay, so is there a start here? There is no start. Okay, so nothing is happening over here. Though the forces are larger, you should explain why this does not happen. Let me make it 1.2. Then this should be, sorry, 1.1 only it should work, not 1.2, because there's a run here. right? When you run it across here, the pulley is now rotating over here, okay, and then the object moves down, and you would be able to find out what is the time taken for the object to come down, what is the distance it has moved. Based on this, you can find out what is the acceleration of the object, right? And compare it with the acceleration which you obtain from the free body diagrams. Okay, you can ask them to match these two and find out, okay, whether the math that I have done is correct or incorrect, right? So, these kinds of things will help them out to perform well in the IA. Okay, so the major purpose of carrying out any simulation without, if you do not have a lab, or even if you have a lab, okay, if you give something like this and ask them to do it, it will really help them out to do well in their IA, because they'll get to know practically how to work on it. Okay, this is how it will be useful. Okay, now I can increase this, I can decrease it. Maybe I'll just click on this. I'll pull this here and make it over here. I'll remove the run, so anyway it will not run. Now I can increase this value also, make it 1.8 kgs over here. This 1.8 is 1.1, so therefore this downward force is larger than the upward force. So definitely this will come down, right? And you once again get a graph of this. So you can do all this. So you can ask them to plot a graph of different masses and see, okay, how does the plot actually change? Your distance time graph, how does it change? What is that you expect from here? Do you get a linear plot? Do you get a non-linear plot? If you get a non-linear plot, what is the reason? Okay, how do you calculate the acceleration, tension? Okay, you can get to know about all these things over there. Okay, now let us move on to this one over here. So the math behind is already given. You can ask them to look into it and then understand it. You can ask them to download this value as a CSV file. Okay, you can ask them to analyze it. Ask them to put a line chart. Okay, introduce an uncertainty of 0.1 centimeter. Okay, you can do all many things out of it. Okay, now let us move on to the next one. Now tension once again. Pendulum. Now, why does a pendulum move in a to and fro motion? This again depends upon the tension and the bob over here. So what we can do is we can pull this to any extent over here. So I can also increase the length over here. See, I can change the angle, I can change the length over here. Let me keep at this length over here, and then I can click on run over here. When I run this, now this is what I can get. But I'm not finding out, okay, anything over here, right? I'm only able to visualize what is happening to the pendulum. Okay, now what I will do is, it's slow over here. I'll let it be slow because I want to view something. Let me click on gravity. When I click on gravity, as I change the length of the string, or maybe the what you call the tension in this, or do whatever I want, let me click on this one once again. If I keep it here, will the mg change? Mg doesn't change. Mg is the mass of the object, right? Weight of the object. Now let us look at tension by gravity. Okay. Now let me run this. Now what's happening to the tension over here? Tension is seen to be maximum here, 1 mg, and as it keeps on going upwards, tension is changing over here, right? Now what I will do is, let me increase the length of the wire. Let me keep it over here. I will increase it. At the mean position, it was 1 mg. Remember this? Okay. Now let me run this once again. Okay, 0.7, 0.8, 0.9, 1 mg once again. Okay, so tension is now independent of the length of the wire. That's what we can understood. And this tension is measured because of the weight of this one here. Right. Now let me calculate the centripetal force also. Now look at the centripetal force here. Centripetal force sometimes becomes 0, sometimes it is higher, sometimes it is lower, and so on. You can get to know about this, and then you can find out the net force. Now what happens to net force? Net force here is seen to be shown by the pink color one. See, the net force keeps on fluctuating over here because it depends upon the centripetal force. It is nothing but your measure of the centripetal force, okay, which is nothing but the tension minus mg. Okay, that's what we can determine from here. So you can do a lot of things using this. Okay, again, okay, it could be used in your SHM. You can use this experiment in your circular motion, or maybe in understanding the tension. Okay, all the three concepts you would be able to explore using this. To the next. Okay, let me move on. Now tension in a wire like this. So to run this experiment, you need to have something called as a Wolfram Builder, I think. Okay, I just downloaded this. I don't know if that's been done. Yeah, it's done, I think. So let me go to launch. Let's do it. It's around 1.5 GB. So you can download it. I don't know. I have not used this. But let me try it out to see whether it works, because it takes a long time. Performance status. max downloads. Okay, let me open the simulation that I have already downloaded. No, wait, just a minute. Let me see what's happening over here. There's something still running at the back. Oh, it still has to install. Okay, let it install. By the time the installation gets over, we'll come back to this. Let me look at the next one. Okay. Now this one is a combination of all the three parameters: tension, friction, inclined plane, air resistance, whatever you want. Okay, everything can be added over here. So tension. So what I can do is I can increase the tension here. So how do I get the tension here? There's a rope here, or the string over here, and the object is being pulled like this. Okay, and then let me put the, initially what I can do is I'll put this theta to be equal to 47.3 degrees. It's nothing but the way how I am pulling it. There's no incline over here. The way I am pulling it over here, friction is 0. Let me start this. Okay, now you see the tx value and ty value are unknown, are not being shown over here. You can calculate this. The angle at which it's been pulled is shown over here. The velocity, how does it increase, is being shown over here. What is the acceleration? Okay, now what I want to do is, okay, let me reset this once again. If I change the tension, how do I change the tension? 37 is there, right? Let me make it, so I'll start from something like around 10 degrees. Where is it? I'll first start with 0. When I start with 0 and find out what is the tension, the object does not move, right? Okay, there's no acceleration. Let me keep this at tension equal to 10 degrees with the same angle and see what is the acceleration. Acceleration is going to be 1.7. Maybe I can have a timer. I can find out in what time this one actually crosses this. Okay, and I can find out like what is the acceleration, what is the mu over here. I can compare with this. I can do all these things over here. Anyway, mu is 0 over here. Okay, and then let me pause this. Okay, now let me say, for example, if I do the same experiment with a different value of mu, 0.1, 0.2, 0.3, and so on, with a given value of tension and a given value of mass and the angle, now how does the graph change? Okay, so you can look at all this. What is the graph you're going to plot? You're going to plot a graph of the velocity versus displacement. Okay, and if you are able to measure the, okay, you will not be able to measure displacement over here. You'll be able to measure something like what is the velocity for each value of the coefficient of friction. You can do that, or maybe acceleration versus the each value of the coefficient of friction. You can find out like how does it change, right? So that is one thing which can be useful. Okay, now let me move on to the next one. Let us see whether our print is completed. No, next one. Let me go on. Static and kinetic friction on an inclined plane. Once again, a mix of it. So you have an friction and you also have an inclined plane. You can change the inclined plane here. You can change the value of mu s, mu k, angle over here, and then you can start this. So vector is start over here. So therefore now initial velocity is a -5 it's given. What happens when it is -5? Which means what? +5 is like this. -5 should be like this. So which means the moment I release it, it should go upwards, right? Does it keep on going upwards? That also we need to look at. Let us start this. Okay, by default it is, I'd been kept like this. Now when I do this, it starts from here, it goes to that point, and once again it has to come down. But why is it not come down? Okay, it stops there, right? The reason is maybe the friction is too high. It doesn't allow it to come down, which means the friction acted at 2 points, 2 places. When it was going upwards, friction was acting downwards. Okay, when it was coming downwards, friction was acting upwards. Okay, now if that is the case, the friction should be the same, right? So why should it not come down? Because when it came down, the gravitational force was acting, okay, but friction was acting upwards. Let us reset this once again. Let us look into this once again. So where is the frictional vector acting here? See, friction is acting over here. Friction is acting over here. The moment it came over here, static friction was acting over here. So why doesn't it come down? Because static friction is larger than the dynamic friction. That's what you can explain here. And then if you want, you can change any of the parameter and see how does it light. Okay, see, the interest in all of these experiments is not to just look at the visualization. Visualization, you can have it anywhere. You can have wonderful visualization more than this. It is about conducting an experiment, jotting down some values, and then trying out, okay, some graphs, understanding what do these parameters give, why do they change, and that is what is the interest. Okay, and see to it that, okay, it is not just clicking something and getting an answer. Garbage in and garbage out will not help you do anything. Okay, so therefore what you need to do is you need to arrive at some meaningful patterns over there. Okay, that is where this will help you. Okay, now let me move on to the next one. This you do it. Okay, I'm not going to do it because it's quite easier to work on. So I'm not going to do the full experiment here. Okay. Next. Once again, the same thing. Okay, but the only thing is the visualization. I liked it very much. That's why I put it over here. So what I can do is I can fix the angle here. There's a slider. I can change the angle over here. I can change the mass. But what is important is this friction here. See, when I say the friction is larger, you see a lot of what you call irregularities, or what you call the surface is very rough over here. Okay, when suppose, let me say for example, I reduce this. Now when I reduce this, still it is there. I can look at the energy also. I can click on this energy. I can find out what is happening over to the energy, which was not available in the previous one. Okay. Now, how do I run this? I can start a replay. And then what I can do is I can keep it like this and I can give a start. When I give a start, it's not moving at all. Potential energy is high, kinetic energy is zero, last energy is zero. What's happening over there? Why? The reason is because friction is too high, so it is not letting the object to slide down. So what should I do to let the object slide down? I should either increase the angle of the incline, or maybe I should reduce the friction. So as a change, what I will do is I'll change the angle of the incline. Instead of 30, I'll make it a little bit higher. Now when I do this, is it moving? No, it's not moving, right? Distance is zero. Once again, I just little bit moved a little bit, but it's still not up to that mark. It's not going. Let me increase it a little bit more often than this. Will it slide? Let me look at this. How much did I increase? I made this only 39 degrees. No, it did not increase. So still, let me increase it. Wow, now it is sliding, right? It's sliding over here. So kinetic energy is so much. Potential energy was zero. As it reached over here, there's some amount of last energy over here, right? So what you can do is you can now verify, you can now find out how does the last energy change, okay, when the angle of the incline is increasing. Is it, so we can now say, because I don't have any numbers to calculate here, I can only say something like this value is only something like 1/3 of this whole box, right? Last time is 1/3. Now if I increase this angle, let me make it like this over here, okay, and let me replay this and let me start here. So what is the angle? 82 degrees, very high angle. When I do this, it came down, the last edge is lesser, right? Then the angle of the incline is higher, last edge is much lesser. When the angle of incline is lower, last edge is higher. Okay, now what I'll do is I can also do something like I can keep it over here. I can reduce the what you have here, the friction. Where is the friction here? The friction coefficient of friction is here, mu k. Okay, I'll make it initially for 0.1, and I want to find, okay, so for this value, how does the what you call the kinetic energy, how is the total energy being lost? Okay, let me replay this, let me start this. See, whatever you are not learning in your textbook, okay, whatever is not there in your textbook also, you'll be able to explore. So students would be definitely able to do very well in their exams. Okay, let me click here. The object is not moving. Now let me increase the angle. From 14 degrees, I'll make it as 24 degrees. No way. Let me start this. Is it moving? No, it's not moving. You might ask the question, at what angle does it precisely move, right? Do the math and get us know, okay, what is the angle at which it moves. It doesn't move. Make it 30. Replay. Start. No motion. Let me increase it a little bit for more. 40. Replay. Start. No way. Oh my god. Friction is still higher, right? What's the value of friction I've chosen? I've chosen only 0.9, I think. Oh, it is 0.1. 0.1 coefficient of kinetic friction I choose. Aha, see, this is 0.9. 0.9, right? Forces this value. Shall I reduce this? See, this is what I didn't do it. Static friction was too high, right? So because of static friction, high static friction, it was not able to move. Okay, so if I make it as 0.1, for example, 0.2, this is only for angle. Okay, I can change any one of them and then find out, like, okay, what happens over here. Okay, all this time I was only changing this coefficient of kinetic friction. But to start with, okay, there's a starting trouble there, right? So you need to actually push this, okay? Fine. Now let me move on to the next one. So you can explore a lot of things using this. It's a wonderful tool. It's in physicsclassroom.com. So anyway, I'll put the links over here. You'll be able to look into the video, know how to use it, and also you can practice it on your own, right? This one, I don't know what's happening to this. It's open. Okay. Now this one, why did I choose? So initially, when you start this, you will not get this protractor over here. And refresh this. I only made this. Sorry, I did not make it. I just adjusted the settings. I do not know anything about the how to code or do these things, because now white coding has come. I'm planning to do something, but it takes a long time. But it's really wonderful to see people who have coded scientifically what all they can do. They have done it. Array, open it here. It's not opening. It's a GeoGebra one, so it takes some time to open. It is open. So this is how originally it looks like. Now what I can do is, this is useful because, all this time we had been doing the inclined plane problems only in Earth. Now let me go for a new planet, Planet X. That's why this was amusing to me. And then what I can do is, I can say release over here, the object does not move. Why it does not move? Because there's no force applied on any object over here. I'm not able to see the object at all, right? Okay, now what I will do is, I will restart this. Now I will take an incline. I'll go for a protractor. When I click on this protractor, I get comes like this over here. This is the object over here. Now I will lift this one upwards over here. Why is it not lifting? Plane angle. Sorry, I had to incline here. I had to move here. So I lifted it here. Let us say, for example, I lifted it to some 30 degrees. Okay, see to that exactly to 30 degrees. And then I have kept material 1. There's some friction. I'll not introduce friction. Friction is equal to 0. Static friction is 0. And I'm doing it on planet X. And now what I do is, by doing this experiment, I'll ask my students to find out what is the acceleration due to gravity on that planet. Release it. It comes down. And the question is, I have got the time here, and using this, can you find out what is the acceleration due to gravity? And is there anything else that you need to find out using this? Okay, we'll ask this question and ask the student to work on it. Okay, and maybe if they are not able to do it, repeat the experiment with this, and maybe by unitary method, will they be able to get the value? Okay, so you can also ask them to do something like this. Okay, next let me. This one, why I had chosen this is because in mobile it looks very well. So if you can download this app into this mobile, what you can do is, instead of tilting the screen over here, for example, if I want to tilt here, I can take like this, I can tilt it here. Sorry, I can move like this. How do I increase the tilt? Tilt is here. Tilt is here. I can tilt it like this. I can tilt it like this over here. And then I can use my mobile. I can tilt it in this way. To see to the object actually moves down. Okay, the similar way what we do for gaming. And we can find out what is the time taken to run and so on. But that was not interesting for me. But what was interesting here is that, look at the angle here. When I tilt it like this, what's the angle here? The tilt is shown here, minus 38.4, minus 38.4, minus 50, minus 54, and so on. Now, when I come back here and I do the tilt in this direction, minus 2.6, in this direction, it seems to be positive. Now, what is this? Is it the same terminology that we actually follow, or do we follow a different terminology? Okay, that's one thing which you need to note it down. Okay, before we start an experiment, these things one has to look into it. Okay, now what we do is, what is that we can determine from here? I just been telling you only about the settings. Let me keep it at some point over here, and I can change the value of mu s over here, mu k over here, static friction coefficient, kinetic friction coefficient, and I can click on this and see whether the object moves or not. The object is not moving. It also shows you the free body diagram, which tells you what is the normal force, what is the weight which is acting over here, what is the frictional force which is acting over here. So as a result of it, okay, what you can do is, you can ask the student to take a printout of this, and then what you do is, you ask them to map these lines. Okay, so and then find out, okay, whether this is equal to this, and why this is not coming down. What is the reason for it? You can ask all these things. Okay, now let me take it back to this one here. And then let me increase this angle to some extent here. Oh, sorry, I need to increase it like this. And then I can change this value mu s to be around 0.3 and see whether it works or not. You think it works? What is wrong in this? Why it shouldn't work? Why it should work? Why it should not work? The reason is, see this value mu s is equal to static is 0.3, kinetic equal to 0. It was only 0.4. Okay, it automatically changed to 0.3. Okay, while you write software, this should be taken care. Okay, anybody can write any software, but while writing for physicists, okay, so there's a limit over here. See, this mu k should always be lesser than mu s or equal to mu s. So therefore, so this is something which you need to look at. And when you change this, automatically the object slides. Okay. Now let me move on to the next one. Let me see, our friend has already downloaded. Still it's going on. Let me go to the next one. This is an extension of the same one, okay, from a different website, and it's from Hawaii. Now you see here, you can change the angle of the incline, mu k, mass. You can change the value of g also. Then I asked you to get the value of g, okay, from a different planet. Now I can change the value of g. I can actually, the value of g is 9.8. Now what I will do is, I'll give it a 2.4 or 1.8 over here and ask it to run. It's going upwards. Why is it going upwards? Look at the value of v naught, -5, right? But it went upwards and it's once again coming downwards here, right? Because the static friction is not up to that mark. So therefore, it is now able to come downwards over here, right? So if we are doing the same thing on Earth, okay, let me repeat the same experiment. Now what happens? It goes only to a little extent and comes down. It doesn't go to that length, right? So you will be able to vary a lot of parameters and try to understand how does the inclined plane work, how does the friction work, okay, in other planets. So this is what you can do with this. Next, okay, buoyancy. So we have discussed about all the three forces. The next one is, the last one is a buoyancy force, which is this here they have included in IB. Okay, buoyancy force. Now you see density of the object is given, density of the fluid is given here. Free body diagram can be shown over here. Volume above the fluid, volume below the fluid of the object, animation speed, everything can be controlled. Now when I click the run over here, nothing is running, right? Why? Because I already fixed the values, nothing should run. The buoyancy force and empty force are equal in nature here. Let me decrease this value. Now what do you expect? When I decrease this to 1.9, what happened? The object started coming upwards. Why did it come upwards? Because this density is lesser than this density, and this volume, this value. So if this is the case, then what can happen is there will be an upward force more as compared to this, and hence, okay, the volume will adjust itself. The buoyancy force is given by density of the object immersed inside the fluid multiplied by volume. Sorry, density of the fluid multiplied by volume of the object inside the fluid multiplied by g. Okay, so if you take these, the volume of the if the density is now reducing, so automatically I made a mistake, I think. Okay, I said density of the object multiplied by the volume of the object inside the fluid multiplied by g. Okay, so therefore, when the density is reducing, automatically your buoyancy force should also reduce. Okay, and if that has to equal to mg, so automatically what happens is this will go upwards over here. So this is why you see volume about this will be different as compared to this. You can ask them to write down, find out the volumes or values of the buoyancy fluid and then get the answer. You can click on this show numbers to get the values of the buoyant forces over here. You can change the fluid viscosity over here and find the effect of this. Is there any effect which has been shown? Okay, you can ask all these questions. You can pull this one. No, you cannot pull. Maybe in the next simulation, you have a wonderful simulation as compared to this. You can try with that also. Okay, so it's a very simple one, but still, okay, for lower classes or even for until 11th and 12th also. The first preliminary one, it is really good. Go on to the next one. This, I liked it very much. So here you have the block density, and below you have the liquid density. You can change both of them. You can find out, okay, there's one more over here. You can find out the value of gravity, that is the weight. You can find out the buoyancy value. You can find out the net force. Okay, now what I'll do is, you can put it for different objects. I'll put it styrofoam. Put the styrofoam. See, the styrofoam is now seen to be floating completely on the liquid. Of course, part of it is inside. Now the liquid here is honey. Instead of honey, if I use this as a gasoline, You see, part of it is inside. If I put it in crude oil, now you see, still almost it's the same. Olive oil, no change. You can find out this also here, right? So net force here, so it's not much of change. Honey, it's upward, it's floating upwards. Nitric acid, no change. Mercury, no change. Okay, almost it's upwards over here. Because the mass of the styrofoam is much lesser. Okay, very, very lesser, definitely it will float. Density is much lesser, not even mass, density is lesser. I'm sorry, I'm wrong. It should be density. Then wood. Wood, as you see here, gasoline, it is completely inside. Why is it inside? You can ask this question, right? Because the density of wood is nearly equal to the density of the gasoline. Crude oil, it's slightly upper. So what does it mean? Density of wood is lesser than the density of crude oil. Olive oil, again the same parameter. Water, higher. Honey, definitely. Nitric acid, up. Mercury, it's completely floating. Ice, you can do it for plastic. You can do it for each one, every one of them. And you can ask them, okay, what is the reflection based on this? Okay, so these kinds of things you can get to know more about it. How do you determine the purity of a substance? Can we determine the purity of a substance using buoyancy? Okay, so these kinds of questions can also be asked. Move on to the next one. Buoyancy. So here once again related to buoyancy. So here this is about, you can vary the density of the fluid, and there's a hand with a spring balance over here. You can pull it with your mouse. When you keep it over here, this gives you only the mass of the object in here. Okay. When you put it inside the fluid, let us say I keep it over here. So what was the value here? It was 110. When it put it also inside over here, it is 87.6. It is now changing over here. See here also, when you keep it over here, the mass of the fluid was seen to be 500 grams. When you dip this one inside, it is 519 over here. So 19.7 ml has been dipped inside. Now when you keep on pulling it downwards like this, when you keep it over here, it is weighing much lesser. So what is apparent weight? You can ask about them. You can find out, okay, what is the density of this, making use of all these parameters. You can ask many questions. Okay, so they should match. You can change the density and then ask them to graph. See, any experiment you do, okay, always see to it that you follow this with the data collection and as well as ask them to draw a graph. So definitely it will help them out a lot. Okay, so if possible, try to introduce some uncertainties, get that data, put it into an Excel sheet, and then add some random variable into it and see to it some uncertainties have been put. Ask them to draw a line of best fit, line of worst fit, and then ask them like whether there is a systematic error, there is a random error. Okay, introduce some outlier. Okay, your paper 1B will become very, very easy. Okay, when you start working on all this. Now let us move on to the next one. This is really good enough. Now what does this give you? For me, everything is good enough. Right. Okay. So now this is a slider here. If I move this one here, now what is that you see? Here the fluid density, I have reduced it. The object density is higher. Okay, object density is high, like iron dropping in water. Now as a result of it, you get this. Okay, so you will be able to see what is the fluid density and so on. Now suddenly you see there's a normal force here. Okay, why does the normal force creep in? Because this object is in contact with the surface. Now let me move this a little bit upwards here. Normal force doesn't reduce. Normal force 81,503, it reducing. Okay, but still, why does it reduce? Because the mass actually reduces, normal force reduces, m into g. Okay, now when I make equal this one to the object density and fluid density are equal. If I keep this to be equal, now what is that you are seeing? The normal force keeps on reducing. Now when I increase this a little bit, now this is the buoyancy force, this is normal force once again. Now if I still increase it over here, I'll come back to this once again. Just wait for some time. Let me look at this and then I'll come back to it. Now what is happening to normal force? 16,700. Earlier it was this much big. Now you see this vector is reduced here. Now still you reduce it, increases. Okay, fluid density is increased. At some point of time, you see normal force completely becomes zero. Make it zero initially. Now I made it zero. Okay, when I made it zero, can you see what's happening over here? This object is not in contact with the surface at all, right? Okay, so it is 85,000 and this is minus 84,000. Okay, the weight, and this is your buoyancy force. So as a result of it, this is now trying to come upwards, right? It is now floating and trying to come upwards because the resultant force is much larger. Now, if I increase this fluid density, definitely the object will start flowing. Okay, now after this you will know about it. Okay, so I need not explain it. Now what are these curves? Let us understand these curves also. Now, if I take this one, let us say this is the fluid density, I change the fluid density to higher value. When the fluid density is very higher, now you see this curve having fluctuation like this. Why is this fluctuation seen? The reason is because this object is fluctuating. When this object is fluctuating, what happens? The object will go inside, will come outwards. When it goes inside, the volume of the object, okay, volume of the object present inside the surface increases. When it's outwards, the volume of the object inside the surface decreases, right? So as a result of it, it changes. Let me, for example, I take this one, I'll drag it upwards over here. Now what do you see here? You see that the object is completely in air. It is not inside the fluid. So what is the buoyancy force? Can you see the buoyancy force over here? This vector, okay, this vector here, it was zero, right? Say for example, show once again. So buoyancy force was zero. Only the weight is acting over here. So look at the graphs over here. The graph here also, the buoyancy force was zero, and you only get this green color one, okay, which is fluctuating. What does this green color fluctuating shows you? It tells you that sometimes object goes inwards, comes upwards. So when it is going inward, there is a buoyancy force. When it is going upward, there is no buoyancy force. Now you see the liquid is in equilibrium with the object, right? So which means what? There is no fluctuation in the liquid surface. So you see the buoyancy force is 84,940, which is a constant. If I pull this upwards, see what's happened? The buoyancy force reduces over here. If I pull this completely outwards, see, it becomes completely zero, right? When I pull this one here, buoyancy force increases. Still, buoyancy force still increases, becomes 33,000. If I bring it inside, it's completely immersed. 39,525, 399,525. If I keep on pulling it downwards, what's happening to the buoyancy force? Is it changing? Buoyancy force doesn't change, right? It keeps on remaining the same over there. Okay, this is what you will get to know about the understanding of the buoyancy force, right? So with this, I think we have come to an end of all the simulation softwares. So like how to use it and what is that we can derive out of it. Of course, there are many more softwares available for the constant forces, but I will not be able to cover most of them because paucity of time. And question is that how many of these tools are we going to use in our classrooms? There's one question here also. Though I show you so many tools, okay, I will not be able to describe all the tools in my classroom. Okay, part of it I'll be doing it. But of course, this is an eye opener because I myself never knew that there were so many tools. Of course, I'm a simulation man. Even my PhD work was completely in simulation. I'm always towards the simulation. But thing is that I never knew that it was so much useful, okay, for the students to understand or to make use of these simulations. Okay, and moreover, in IB especially, you don't have anything like rote learning, and most of them comes only in understanding. And I feel understanding a subject comes by only by doing something. Okay, so definitely simulation will help you out, okay, in doing things. So as much as possible from this year onwards, even I am trying to put it across into my lesson plan. Like, okay, so before starting a topic, how to start it with a simulation, give that to an student and then ask them to work based on it and thereby understand it, reflect on it. Because most of the time we always go by reflecting only. Okay, but that actually increases the understanding capacity of the student. Okay, much of talk, more than half an hour. We'll stop here and we will see the next video would be on variable forces like string force. What else do we have in variable force? We have air resistance. Air resistance we already covered over here. Okay, I'll just give a glimpse of it. Okay, before that, let me see. This has been done. Wolfram prayer has been done. Okay, let me just try to open this. This one we didn't look into it, right? I will share my screen. Just a minute. Just give me a moment. I'll just share my screen. This was about the tension, right? Right. The last one, which I missed it out while we're doing because I had not installed this. So this is the mass. I can change the mass of this. I can change the angle here. As I change the angle, how does the tension change? you can look into this. So recently also, I think November 2024 paper, I think there was a question on this on an MCQ wherein you have a string, you have wire, and you have a bird which has been sitting on top of it, and ask them to find out like how do you resolve the two forces, right? Find out the weight of the bird and so on. Okay, so you can do these kinds of things also. Okay, you can click on unequal over here. You can see how does it work over here. Okay, you can pull this one. No, you can't pull this. You can only change the angles over here, right? So this is what you can do. There are many such simulations available from Wolfram also. You can look into it also. If I get to know much more, I'll just put it across here. Okay, so with this, I think I'll stop here and continue with the next session, maybe today evening or maybe tomorrow. Okay, thank you. Thank you very much for being with me. Do like, share, and subscribe to my channel, and share these videos with all of your colleagues so that YouTube also recognizes my channel for other actions. Thank you.